Hello and welcome to this ongoing lecture series on thermodynamics. We have been looking at a thermodynamic framework from very scratch, very beginning, and in that we are at the juncture of discussing what are called Maxwell relations in this particular lecture. So as part of this thermodynamic framework, let's ask ourselves what have we done so far, sort of a recap for the past 5 or 6 or 7 or so videos that have been uploaded, lectures that have been uploaded. We have defined the following. We started with systems, subsystems, surroundings and boundaries between subsystems or between systems and surroundings that essentially dictate the nature of interactions between them. By interactions, we mean modes of exchange of energy between these entities. Then we define the state of a system either from a macroscopic perspective or a molecular perspective by defining the energy of the system. We started with defining the internal energy, and then we also said later that the state of a system, whether macroscopic or molecular, can be defined by defining its entropy. We understood what it means for a system to be in equilibrium. What it is, that it is one of the rest states, and what it means to be in equilibrium. We understood entropy and how it is connected to multiplicity, which essentially is the measure of the number of molecular arrangements or molecular states that correspond to a measured or studied macroscopic state, right? So this is what we sort of understood by entropy. And then we also looked at entropy as energy dispersal. So given that there is a certain amount of energy stored in the system by way of various molecular arrangements through potential energy or kinetic energy, in what form is that energy stored? Per degree of freedom, how much energy is available? Is it concentrated in a few degrees of freedom, or is it dispersed in more numbers of degrees of freedom, or more, which degree of freedom are you looking at? Is it in terms of constraining the positions, relative positions of atoms or molecules by way of some sort of a bond which results in some sort of a potential energy, primary or secondary bond? Or is it in terms of kinetic energy? Is it in terms of what modes of kinetic energy are you looking at? Is it available for all the molecules? In what form? So that dispersal also is a sort of a consequence of this sort of a multiplicity that comes from the measurement or study of a macroscopic state of a system, which uses very few variables to study a system which is comprised of various molecular arrangements, to describe which exactly we need a very large number, more than Avogadro number of variables. So we sort of understood entropy and multiplicity and energy dispersal. So we looked at various forms of energy of the system, starting from internal energy, and then in the last lecture we looked at how enthalpy, Helmholtz free energy and Gibbs free energy arise. We looked at various processes, reversible, irreversible processes. We also looked at energies in transit, which is the measure of energy that is exchanged through a process between subsystems or between system and surroundings through the boundaries, which we identified two types of energies in transit. One is heat, the other is the various work modes, out of which we have considered so far moving boundary work and species exchange work. We defined the extensive properties. Well, we took these for granted: volume of a system in number of moles or number of molecules of species that are present in the system. We had a fairly detailed discussion on the intensive properties, temperature, pressure and chemical potential, which arises partial derivatives of internal energy as a function of its independent variables, namely entropy, volume, and number. And we also looked at how these what is the physical significance of these three intensive properties. We looked at the criteria for thermodynamic equilibrium. We showed that the intensive properties have to be constant across subsystems or across system and surroundings for them to be in equilibrium. So, so an isolated system is where this sort of an equilibrium does not exist between the system and surroundings. When the system is not isolated, which means that it has at least one boundary through which energy exchange is possible, then this criterion of this thermodynamic equilibrium, depending on what modes of energy exchanges are available through that boundary, so those intensive properties will become constant across the subsystems or across both sides of the boundaries, right? And then we looked at the various fundamental equations of state, like du is TdS minus PdV plus mu dN, or dH is TdS plus VdP plus mu dN, and so on and so forth. And then the integral fundamental equation of state, which arises from the nature of the extensive and intensive properties, homogeneous functions of first order and homogeneous functions of zeroth order. And therefore we wrote u equals PV u equals Ts minus Pv plus mu n, and so on and so forth, right? So we have done all of this so far. Now we are going to ask a specific question. Now we are going to discuss thermodynamic properties. Among the various properties or functions or the variables that we have been discussing that specify or define the state of the system, which of these can be measured using practical experiments? For example, it is possible to measure volume. It is possible to measure temperature. It is possible to measure pressure. So there are certain properties that can be measured. There are certain other properties or functions that are not easy to measure using practical experiments. Among the extensive properties, volume, area, length, so basically size, scales, and amount of substance, right? These can be typically measured. Among intensive properties, it is possible to measure temperature and pressure. It is not very easy to measure chemical potential, but it is possible to measure concentration. For example, amount of substance per unit volume, or amount of substance per unit mass, for instance, right? So a specific substance per unit mass of the overall system, so to speak, right? Concentrations can be measured also, even though they are not listed here. Energy added or removed to or from the system, which is energies in transit, they can be measured in indirect manners. So you can look at some heat source and it is supplying heat, or you can look at heat sink, which is removing heat, and then you can look at what is the change in the temperature of that heat source or heat sink, for example, like you would in a double pipe heat exchanger, in some form of heat exchanger. So, and then you can look at that temperature change and decide how much energy has either been added or removed from the system. Forces and surface tensions can also be measured indirectly by basically measuring some sort of an effect of that force or surface tension on the surroundings, which has to be carefully designed, right? So the key is, many of the rest of these properties are not very easy to measure directly. Therefore, we need to utilize the thermodynamic framework that we have developed so far to develop relations between these measurable quantities, so that principles of thermodynamics can be applied to practical problems. So this is going to be sort of the focus of this particular part of the lecture. And then there is one more part where we will discuss various properties, how we obtain those properties, and what sort of relationships can be established, especially with respect to measurable quantities. Okay, so that will be the focus of the rest of this particular lecture. Some of the common such relationships that are sought in thermodynamics are PVT relationships, which are relationships between pressure, volume, and temperature. They are often expressed as what are called equations of state. A classic example which you've probably heard of before is the ideal gas equation of state, which says P into V is equal to N into R into T, where N is the number of moles of the substance, R being the universal gas constant, and temperature being T being temperature, right? So there are these kind of PVT relationships, and then various other defined thermodynamic properties. In addition to the thermodynamic properties we have seen, we are going to define a whole set of thermodynamic properties in this lecture and the subsequent ones. And in doing so, often we use molar properties in such definitions. These molar properties are intensive properties. So basically you can talk about volume per unit mole of a substance, volume occupied by 1 mole of a substance, that's called molar volume, right? But typically intensive properties, of course, since they are independent of the size of the system, there is no such molar properties for intensive properties. For extensive properties, of course, we can have molar properties. So note that molar properties are defined only for extensive properties. Instead, intensive properties are independent of the size of the system, right? So these are defined per unit mole of substance in the system. Suppose N is the total number of moles of substance, all the species together, if the system is a multi-component mixture. If the system is a pure single component system, then the total number of moles in the system is simply equal to the total number of moles of the only substance that is present in the system. So we look at the total number of moles always. So then we have molar internal energy, denoted typically by the lowercase letter corresponding to the variable that is used for the extensive internal energy, right, or any other property, right, extensive property. So U, small u, lowercase u is simply uppercase U divided by N. Molar entropy therefore is the total entropy by N. Molar enthalpy, similarly molar Gibbs free energy, and so on, molar volume. And note, for a single component system, molar Gibbs free energy at constant temperature and pressure is simply the chemical potential, because there is only one component. So when you take the derivative of the Gibbs free energy with respect to that total number of moles, there is only one component, and therefore that will simply become the chemical potential. So before we start these obtaining thermodynamic properties of various, for example, we will try and relate internal energy as a function of measurable quantities such as temperature and volume. Internal energy, the independent variable has been entropy volume number. So instead of that, we'll take molar internal energy, for instance, and relate it to temperature and volume. Similarly, molar enthalpy, we will try and relate it to temperature and pressure rather than entropy and pressure. So before we do such, develop such relationships, we need to, we are going to have to utilize some of the mathematical tools that are available in partial differentiation for this purpose. So that they are all listed in this slide. None of them is derived, none of them is proved. You are recommended to consult various mathematics books, typical calculus books like Thomas calculus books. They would all have this discussed in fair detail, all right, or even probably advanced engineering mathematics by Erwin Kreisig or by so these are typical Michael Greenberg are excellent books to refer to for these details. So one is chain rules of partial differentiation. So if you have f is a function of x comma y, then df, this is the definition, this is how you get your partial derivatives, right? The differential in f can either be due to differential in x or differential in y, and then you define the two partial derivatives. Now if I want to take a derivative of f as a function of some other variable a, then this is my chain rule. Dou f dou a at constant y is simply dou f dou x at constant y times dou x dou a at constant y, and since y is held constant, this term will drop out. Now if I were to do the other way, dou f dou y at constant a, which is then going to be dou f dou x at constant y times dou x dou y at constant a plus dou f dou y at constant x. Basically it's sort of like taking this sort of dividing this throughout by dy, so to speak. Right? These are chain rules. And then there is a cyclic relation. So for example, if you have x, y and z, all right, they are interrelated. So this product is equal to -1. This is a very useful relation that we will utilize in this and the subsequent lecture. Dou x dou y at constant z times dou y dou z at constant x times dou z dou x at constant y. This product turns out to be -1. So now, as part of developing these thermodynamic property relationships, we need to we are confronted with this Maxwell relations. These are something that become very useful in converting some derivative, some quantity which may not be easily measurable into some other quantity which is much more easily measurable. And Maxwell relations play a major role in this. So first, what I'm going to show is how these Maxwell relations arise. All right. So let's start with this. Maxwell relations provide the necessary prelude to developing relationships among the various thermodynamic properties. So to get Maxwell relations, this is how we are going to go about the process. Suppose we start with, again, f of x comma y, where x and y are independent variables. Then we know that the mixed second partial derivatives. So this is the mixed second partial derivatives. So this is basically dou by dou x of dou f dou y. What is this dou y of dou f dou x? So here the first derivative that is taken is with respect to x and then with respect to y, whereas here it is the other way around. The first derivative is taken with respect to x and y, and the second derivative is taken with respect to x. These two are equal. In other words, it doesn't matter the sequence in which you are taking these derivatives, because these two are, independent variables. So now let us consider this molar internal energy. So du is TdS minus PdV. I have not taken UDN because everything is differentiated with respect to, or sorry, defined with respect to constant n per unit mole, and therefore n doesn't change, the n drops off. So we have du is TdS minus PdV. Note that it is the extensive variables alone that have become molar quantities, and this is all therefore intensive quantities. Now this basically, so u is a function of now s and v, two independent variables, and therefore I must be able to write dou square u by dou s dou v. So in the sequence where I first take a derivative of u, internal energy, with respect to volume, and then with respect to entropy, should be the same as taking the derivative of molar internal energy with respect to entropy first and then volume. So there should not be any difference in this. So now if you look at this, dou square u dou s dou v, which is this, is basically dou s of dou u dou v. So of course when you take this partial derivative, it is of course conditional that the other independent variable is held constant, and similarly when you take the partial derivative with respect to entropy, the other independent variable, which is volume, is held constant. And look at this, what is dou u dou v at constant s? Dou u dou v at constant s is simply minus p, and therefore I can substitute for this partial derivative minus p, and therefore the left hand side is minus dou p dou s at constant v. So similarly, for the other mixed partial derivative, you are now taking a derivative with respect to entropy first, which is the inside, the first one, right? Since du is TdS minus PdV, this is taking a derivative with respect to entropy, keeping a volume constant. So therefore this has to be temperature, that is the partial derivative, the first partial derivative of u with respect to s at constant volume, that is temperature. So this mixed partial derivative becomes dou t dou v at constant s, and therefore we get the equality of the mixed partial derivatives, resulting in this particular relationship minus dou P dou S at constant V is plus dou T dou V at constant S. This is the Maxwell relation for internal energy. Similarly, I can write this to be enthalpy, Helmholtz free energy, Gibbs free energy. I'm not going to show all those steps. I will leave it for you to derive those Maxwell relations, but I'm just going to show what these relations are. So this particular mixed partial derivative, dou H dou P first, is going to result in volume, dou H dou S is going to result in temperature, and so you get the Maxwell relationship for enthalpy. And similarly, when you look at dou A dou V, right, dou A dou V is negative minus S, and dou A dou T is, I'm sorry, I think it is the other way around. Dou A dou V is pressure, minus pressure, and dou A dou T is minus entropy. So anyway, you will get the same relationship. Both will have negative signs and they will get cancelled, and therefore you will get a Maxwell relation for Helmholtz free energy. And finally, similarly, we can write a Maxwell relation for Gibbs free energy, and I would have you please derive these for yourselves. So these are useful relations. Now in this, of course, I have not considered the number of moles of a system, right? So therefore we have been looking at all these properties, all these extensive properties have been converted into molar properties. But now if we had number of moles as well, considering still only one quantity, right? So then you can have three independent variables, right? So just as you had one relationship for Maxwell relation for internal energy, which consider a pair of variables, entropy, volume. Similarly, we can have volume number, entropy number. So instead of one Maxwell relation, there could actually be three Maxwell relations for, when you don't consider the molar properties, right? So you can write those three, similarly 3 for these, 3 for these, 3 for these, 12 Maxwell relations when you generalize this, not for molar properties but for the accounting for the extensive properties also. Now that is presented in the next slide. So these are the combinations. So now for this is given for, of course, Helmholtz free energy. There are three possible combinations: TV, Tn, and Vn. Those are the Maxwell relations, and so on and so forth. There are 12 such relations, and this is taken from this publication. And again, you can derive these. These are all mixed partial derivatives being equated. So the same approach applies. And now if you have multiple components, so then you will have mu1 dn1 plus mu2 dn2 plus so on and so forth, and then you will have accordingly even more Maxwell relations that can come up. And all these Maxwell relations together, taken together, will be of immense help for us when we look at the next part of this lecture, where we derive the various thermodynamic property relations. What are the thermodynamic properties we are going to look at? I am just going to list all of those, and then we will wrap up this part of the lecture. One is specific heat capacities. This is something that you learned. This is basically the amount of energy added at constant pressure. So if it is at constant pressure, then the energy content is enthalpy, right? To increase the temperature of 1 mole, that's why molar enthalpy, of a substance by 1 unit temperature. So this is basically your specific capacity at constant pressure. If the same thing is measured at constant volume, then the corresponding energy, the corresponding thermodynamic potential is internal energy. And since we are measuring this per unit volume, per unit mole, we are therefore defining molar internal energy, and this is molar specific heat capacity at constant volume. So this of course depends on whether the boundary is either moving boundary or rigid boundary. There is also a coefficient of thermal expansion when you are expanding a system at constant pressure, which is an isobaric process, or this corresponds to a moving boundary. How much does the volume of the system change, or the ratio of change in volume to the total volume of the system per change in temperature, per unit change in temperature? This is coefficient of thermal expansion. All of these will be defined in more detail in the next part of the lecture. Isothermal compressibility. So now we are looking at a compression at constant temperature, and therefore this is an isothermal process, as the term itself indicates, and this indicates of course that there is a diathermal boundary, and how much is a reduction in volume per unit volume. Then there is a unit change in pressure of the system. Adiabatic compressibility. Now again, this basically means the process, the boundary is adiabatic boundary, not a diathermal boundary. Of course, this is of course defined at constant entropy. A reversible adiabatic processes, isentropic and irreversible adiabatic processes, not isentropic, because when what we learned towards the end of the entropy lecture, the entropy then will increase, it will not remain constant, right? So the inequality that we have, greater than or equal to, the inequality that we have, that applies to irreversible processes, and therefore if your process can be reasonably reversible and it's an adiabatic, then the process can be approximated as an isentropic process, and for such a process, what is the compressibility of the system? And the next one is Joule-Thomson coefficient. This is an isenthalpic process. A classic example is throttling, and this is something that will again be discussed in the next part of the lecture. And of course, finally, not least, energies and entropy as function of measurable quantities. Your internal energy is a function of entropy and volume. Instead, can we get that as a function of temperature and volume? Enthalpy is a function of entropy and pressure. Can we get that as a function of temperature and pressure? Entropy can be looked at either from this perspective or this perspective. In fact, if you can go back and look at it from all of these both these thermodynamic potentials, you can convert this formulation to the entropy formulation. Of course, so it is not possible to do it with Helmholtz free energy or Gibbs free energy, because the independent variable itself is not entropy, it is temperature, right? But so in this case, so S would have been a function of, for a rigid adiabatic and what is it called, impermeable boundary, entropy in the entropy formulation would have been a function of internal energy, volume and number. Now instead of internal energy, can I measure this as temperature and volume? Similarly, for the when I convert this enthalpy to entropy formulation, then instead of S being a function of enthalpy and pressure, can entropy be a function of temperature and pressure, etc. So all of these will be obtained in the next part of this lecture. We come to the end of this part of the lecture on Maxwell Relations and Thermodynamic Properties. So we have learned about Maxwell Relations primarily in this lecture, and we are going to use these to obtain the various thermodynamic properties that have been defined at the end of this lecture. So as always, I'd be very happy to receive feedback from all of you. If you have any questions, please feel free to leave them on the YouTube channel. Any comments that you may have, any feedback is always welcome, or you may reach me otherwise through my email or other modes of contact. Thank you very much for listening to this lecture. I hope you have a wonderful day.